In this lecture, we are going to talk about the logic behind red-black trees. When we have been talking about AVL trees, it was quite apparent and straightforward that what's the logic behind AVL trees. We have calculated the height parameters, and if we have come to the conclusion that the left or the right subtree has different height parameter, then we know we have to make some rotations. But what's the logic behind red-black trees? Why we have defined the principles like this? So why is that the root is always black? Why all leaves are black, and so on? So how to make sure that with these principles we are going to end up with a balanced tree. And if we consider these two principles, that every red node must have two black child nodes and no other children, it must have a black parent. This is the first principle, and every path from a given node to any of its descendant null pointers contains the same number of black nodes. This number of black nodes is denoted by this M. So, for example, this is a valid red-black tree. As you can see, all the red nodes have two black children, and the parent of every single red node is black as well. And every path from a given node to any of its descendant null nodes contains the same number of black nodes. In this case, this M, so the number of black nodes, is equals to 1. As you can see, if we start with the root node, no matter what path we are considering, there's a single black node. So in this case, the M is equals to 1, and we see that every path from a given node to any of its descendant null nodes contains the same number of black nodes. So let's assume that the shortest path from the root to any leaf node has M black nodes. By the way, the shortest path in a red-black tree contains black nodes exclusively, and the longest path in a red-black tree contains alternating red and black nodes. So black node, red node, black node, red node. This is the longest path. The shortest path contains black nodes exclusively. Okay, so if we want to construct longer path than the shortest one, we can insert a new red node, but because of the first principle, we cannot insert just a single red node. Why? Because every red node must have two black children. Okay, so the longest possible path consists of 2 times M nodes alternating black and red, because every red node must have two black children. So that's why the shortest path contains M black nodes, the longest path contains 2 times M nodes, and because of the second principle, every maximal path have the same number of black nodes. So that's why we can come to the conclusion that no path is more than twice as long as any other path in the tree. So the tree is approximately balanced. It is not as rigidly balanced as AVL tree. We are not going to make as many rotations as we have seen for AVL trees, because as you can see, the longest path contains 2 times M and the shortest path contains M nodes. Okay, so this is why red-black trees are not that rigidly balanced, but this is why it is much faster when we insert items. If we look up items, it has ortho log n running time complexity, but it's going to be a bit slower than AVL tree because it is not as rigidly balanced as AVL tree. For AVL trees, every path has the same length approximately. Here, the longest path can have 2 times the size of the shortest path. So that's the logic behind red-black tree. This is why we can make sure that these principles are not violated. We will end up with an approximately balanced tree-like structure. Thanks for watching.